Hello students, in the previous lecture we had discussed how to find the scalar triple product of three vectors. Now in this lecture we'll discuss the properties of scalar triple product. So if three vectors are given to us in space, we can find their scalar triple product, or the three vectors will represent a parallelepiped. For that the necessary condition is the three vectors must have a conterminous edge and they form a right-handed system. So properties of the scalar product are: first property is, if A, B, C of the scalar product are cyclically permuted, then prove that the value of the scalar product remain the same. That is, we'll prove that scalar triple product of ABC is equal to scalar triple product of BCA is equal to scalar triple product of CAB. Proof for this is, let us suppose ABC represent three vectors with conterminous edges of the parallelepipeds such that they form a right-handed system. Then the volume of the parallelepiped is given by V is equal to scalar triple product of ABC is written as A cross B dot C. Now if the vectors ABC are cyclically rotated on a same diagram or made new diagram for each rotation, every triple product will form a right-handed system of the same parallelepiped of volume B. Now let us find scalar triple product of BCA. BCA B cross C dot A. That will represent the volume B, same volume B, which was represented by the scalar triple product of A, B, and C. That is, scalar product of ABC is equal to B. Now, as shown the diagram, the parallelepiped A, B, C, E, F, G, D. This parallelepiped, the volume of this parallelepiped is V. If we write in place of this, the volume given by parallelepiped given by vector A, vector B, and vector C. V is the volume for this. If you write in place of a B, B in place of B, C, or C in place of C, we write A. So we will get scalar product of B, C, A, B, C, A vectors. Their contour size is O, and they form a right-handed system. Similarly, if we in this place write A, C, in the B we write A, and in place of C we write uh, B, C, in place of B, A, C, A, B. C, A, B, this will represent the volume B, which will be the resultant of the scalar product of C, A, B. So, from first we got scalar product of A, B, C is equal to B. From first we got scalar product of A, B, C is equal to B. Second, we got scalar triple product of B, C, A is equal to B. And third, scalar triple product of C, A, B is equal to B. From first, second, and third implies scalar of ABC is equal to scalar of BCA is equal to scalar of CAB is equal to B, implies the result. Now next property, prove that in a scalar triple product, the position of dot and cross can be interchanged, provided that the cyclic order of the vectors remains same. That is to prove scalar triple product of ABC is equal to scalar triple product is equal to scalar product A, BCA. That is equal to, we have to prove A cross B dot C is equal to A dot B cross C. So for that, for the proof of this, we will use the first property. If ABC are changed in cyclic order, the value of the scalar product remain the same. So we take these two results from the first. ABC scalar product is equal to BCA scalar product. So this is written as this implies A cross B dot C. This implies B cross B dot C. Definition of scalar product. So if we use, we know that the scalar the dot product of two vectors commute. So now we write the right hand side of this is equal to, we can write this A. This is again vector. If we want to take two vector, we get again the new vector. This is a vector. These are two vectors. Their dot product commutes. So we can write this is equal to A dot B cross C. So now, if we conclude, if you see in this final result, we find that dot and cross are interchanged, and the value of the value of the scalar product will remain the same. That is, what we have proved in the first lecture, first property. Sorry. The above equation shows that the dot and cross of the scalar product can be interchanged without changing the cyclic order of the product. Now, third property is prove that change of cyclic order of vectors in scalar triple product changes the sign of the scalar product, but not the magnitude. So that is what will prove. Scalar product of ABC is equal to minus of scalar product of BAC is equal to minus of scalar product of CBA is equal to minus of scalar product of ACB. Now again we'll use the first property of the scalar product. We know that scalar product of ABC is equal to BCA is equal to scalar product of CAB, which will give the volume of the parallelepiped whose conterminous edge, which have these three vectors have a conterminous edge and they form a right hand system. This is a necessary condition for the three vectors to form a parallelepiped. Now we take the first result. This first equation of this scalar product of ABC is equal to, by definition, A cross B dot C. Now this cross product is non-commutative. You know that you have read in the previous class, A cross B is equal to minus B cross A. Substitute the value of A cross B here. This we got minus of B cross A dot C. So minus of, now again apply definition of scalar product. Minus is outside, minus 1 is outside. This is equal to minus of B A C. This first holds true. ABC is equal to minus of BCA. For the second result, we'll take second second equality of the second. This is equal to this. Scalar product ABC is equal to BCA. If we take this left hand side equal to this, now by definition we again write this equal to B cross C dot A. Again in this bracket we'll apply, because this is a cross product. Cross product is non-commutative, or if we change the order of the vectors, means the sign will change. Minus of B cross C is equal to minus of C cross B. We have proved this in the earlier class. So again, minus 1 is outside. So this is the definition of scalar product. We can write this as to C B A. Second result is this. Now third, for the, now prove this is equal to scalar product is equal to minus of scalar product ACB. We'll take scalar product of ABC is equal to scalar product CAB. On the right hand side, we write by definition of scalar product, this can be written in this form. Again in the bracket, we'll apply C cross A is equal to A cross C. Minus 1 is outside. Minus outside means now again minus of C cross A dot B can be written as minus of ACB. From first, second, and third implies that scalar product if scalar product ABC is equal to minus of scalar product of BAC is equal to minus of scalar product of CBA is equal to minus of scalar product of minus of scalar product of ACB, which will result, or this means if the order of the vectors in the cycle triple product is changed, then the magnitude remain the same, but sign changes. This order change, this order change, this order change. The magnitude remains same, but sign in every case changes. Okay. Fourth property is prove that the scalar triple product, the three vectors is zero if any two of them are equal. For the proof, let us go three vectors representing the size of parallelepiped and satisfying both the conditions for continuous size and right-handed system. They form right-handed system. So scalar productivity is equal to, by definition, this is this. If we take, suppose A and B are equal. So first condition, if we suppose A and B are equal. So A and B are equal means we know that cross product two equal vectors is equal to 0. We have proved that in earlier class. So if we substitute this in the first equation, we'll get that A cross, in place of B we substitute A cross A triple product is equal to A cross A dot C. A cross A is equal to 0, 0 vector into C vector is 0. The second result. Similarly, if A is not equal to B but A is equal to C, then in place of C we write vector A. Again, by first property, scalar triple ABC is equal to scalar BCA is equal to CAB. So we take scalar triple of ABC is equal to scalar triple of CAB. But again, by definition, we can write this in form C cross A dot B. Now C cross A dot B, C cross A. Now C is equal to A. If we write this in place of C, in place of C we write A, it is equal to A cross A dot C. A, C is equal to A, or C is equal to A. C is equal to A. So that there will be some mistake. This must be equal to, it should be B. A cross A dot B. A cross A is equal to 0 and this is again equal to B. This is B vector. So this is 0. Similarly, if B is equal to C, in a similar way, we can prove that their scalar product will come out to be 0. Conclusion of this property is, if we are given three vectors in space, any two of them are equal, then their scalar triple product will come out to be 0, means the three vectors will not form a parallelepiped. Fifth property, for any three vectors ABC and a scalar lambda, scalar means any real number, all real numbers are scalars. So whenever we write scalar in this vector calculus, this means this is a real number, any real number. Then prove that lambda times A B C scalar triple product is equal to lambda times scalar triple product of ABC. So for this, we take the left hand side of this scalar triple product of lambda times A B C is equal to, by definition, this is lambda times A cross B dot C. In the earlier class, we have read that lambda times A cross B can be written as lambda times A cross B vector. Lambda times A vector cross B vector is equal to lambda times cross product of A and B vectors. So when you substitute this value in the above equation, we got lambda times A cross B dot C. Now lambda times A cross B dot C, A cross B dot C, C, again by definition of cross product, we can add this in big brackets. This is a big, sorry, these are big brackets. So this implies the result, implies the result. If I see this, if I take lambda t equal to half, so scalar product of ABC was given, will give this up is the volume of this valve. Which valve? O A B C D E G. Now, if I on the right hand side, if I take uh, this scalar product of ABC, right? If I find lambda to be half, then lambda times half will be vector will be this only. Lambda times half is this vector. Lambda half a is this. So lambda times a vector, uh, b and c vector, the scalar triple product will be the parallelepiped O S R Q D E G. This parallelepiped. Now right hand side, scalar product of ABC is whole volume, whole this volume. So half of this will be this volume. So this property. In a similar way, we prove the next property. Next property: if ABC are any three vectors and LMN are any three scalars, scalar means they are real numbers, then lambda times A vector, lambda time L times A vector, M times B vector, and times C vector triple product is equal to product of the three scalars LMN into scalar triple product of ABC. Scalar triple product of A, B, A, B, C. Again, we do left hand side of this. This is equal to scalar product of L A vector, M B vector, and C vector. This is can be written as by definition L A vector, M B vector, L A vector cross M B vector dot M C vector. Now L we have read in the earlier class, L A vector cross B vector is equal to L times A cross B vector. Same result. So when you use this L A vector, L is outside using this L A vector cross M B vector dot M C vector. Now this cross product, if you change the order, like this sign will come L into minus of MB vector B vector dot NC vector. Again, I'll give you this result. M will come out, LM is outside, minus of B cross B, B cross A vector dot NC vector. So if again B cross A is equal to minus B cross A is equal to AB is equal to LM into A cross B vector dot NC vector. So C this is scalar. Scalar can be taken outside similar way to compute them. So outside this implies LMN into A cross B dot C into B cross C. So this is equal to by definition of scalar product, we can add LMN is equal to scalar product of conclusion of this property is if you take if in this property if you take m is equal to 1, n is equal to 1, so this property will become the fifth property, same fifth property. So in general way, if you take L is equal to 1, 1 is equal to half, this is equal to twice, so this is equal to 4 times. So this will become, this is half, this is 2 times, this is 4 times. So this become, this square product become 4 times of the square product of ABC. So you can have so many examples. You can discuss this. We'll discuss when we solve the problem of this. Now next property is prove that the scalar triple product of three vectors is 0 if any two of them, if any two of them are parallel or collinear. Okay? Prove that the scalar product of three vectors is zero if any two of them are parallel or collinear. So let us suppose we set three vectors such that they are A is parallel to or collinear to B. So this is a polarity condition. If two vectors are either parallel or collinear, then we can write then one vector will be scalar times others. So scalar times other or second vector first scalar times first. So let us take scalar product of ABC. This is again equal to definition A cross B dot C. If we put A is equal to lambda times B, A vector is equal to lambda times B vector, or B vector is equal to lambda times A vector. In the above result, we got A vector into the B vector lambda times A. Lambda times A, this is equal to lambda times A cross A, cross product of two same vector will be 0, 0, 0. So if any two of the vectors of a scalar product are 0, implies if any two vectors of the three vectors are either collinear or parallel, then the scalar product will always be equal to 0. And the last property is the necessary and sufficient condition for the three non-zero and non-collinear vectors to be coplanar is that their scalar product must be equal to 0. What is the statement of the statement? For the three non-zero and non-collinear vectors to be coplanar is their scalar product must be equal to 0. So necessary if and only part means necessary part, if necessary part, if part, if and only if part is this, and sufficient part is only part. The necessary part is, we'll suppose necessary means this part, necessary is the necessary part. Necessary part means we'll suppose that let ABC are three non-zero and non-collinear coplanar vectors. Then what to prove? Their scalar equal 0. So what we proved? Scalar equal to 0. So let us suppose scalar product of three vectors ABC is equal to this. By definition, this will become this. Now, from the definition of cross product, we know that cross product of two vectors is always perpendicular plane containing two vectors A and B. But ABC are coplanar. This implies the cross product of two vectors is whatever the new vector was that will also perpendicular to C. So cross A cross B जो new vector जो था that is perpendicular to C means the dot product of A cross B vector and C vector must be equal to 0 because they are perpendicular. So this implies scalar triple product of three vectors equal to 0. Implies that if three vectors which are non-zero and non-collinear are coplanar, then their scalar product is 0. Now sufficient part. Let ABC three vectors and the vectors are non-zero and non-collinear. Non-zero and non-collinear and such that their triple product is 0. Now we will show that they are coplanar. Given is scalar product of three vectors 0 and the vectors are non-zero and non-collinear. So this equal 0 implies definition. This equal 0 implies A cross B. A cross B dot C equals 0. Above equation will hold true if either ये ट्रू कब होगी जब या तो इनका क्रॉस प्रोडक्ट 0 है या C 0 है और A क्रॉस B इज परपेंडिकुलर टू C. बट गिवन क्या हमारे को C वेक्टर्स आर नॉन जीरो मींस वेक्टर नॉन जीरो तो प्रोडक्ट इनका नॉन जीरो आएगा. वेक्टर्स आर नॉन जीरो एंड नॉन कोलिनियर. ABC are non-zero, non-collinear. Therefore, C vector is not 0, and vectors A and B, which are not collinear, therefore their cross product is also not equal to 0. So we are left with, if they are not equal to 0, then vector A cross B must be perpendicular to C. So if it is perpendicular to C, then by the definition of cross product, A cross B is always perpendicular to AB. Now A cross B perpendicular to C and A cross B perpendicular to AB. This first and second result implies A, B, and C vector must be coplanar. Now, conclusion for this is, if three vectors are coplanar, three vectors are coplanar, the vectors are neither non-zero nor non-collinear, then their scalar product will be equal to 0. This is, thanks. Thank you very much.